Swayam Prabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 16. We were talking about how to plot the x bar, the mean from a distribution. So let's, and the standard deviation Sx. So let us actually look at it, the Sx or the standard deviation of a distribution can be represented as sigma xi minus x bar square divided by n minus 1 whole under the root, and this can further be represented as sigma xi square plus x bar square minus twice xi x bar divided by n minus 1. You can further simplify this by looking at this as sigma xi square by n minus 1 plus x bar square again sigma n minus 1, and the sigma, as I had mentioned earlier, is for samples from I 1 to n. So it is exactly n samples. So then we have twice sigma xi x bar by n minus 1. So having said that, we can also try to further simplify it by substituting this as n x square, because you are repeating the x bar square exactly n times here, divided by n minus 1 minus twice of, if we multiply and divide by n, we get this as x bar sigma xi by n, okay. And this can further be represented as root of sigma xi square by n minus 1 plus n x dash square by n minus 1 minus twice n minus 1, and this is actually x bar square. So eventually we can represent this whole thing as sigma xi square by n minus 1 plus n x bar square. I'm sorry, it has to be minus because you have a plus n and minus 2n. So minus n x bar square n minus 1, and this can further be written down as sigma xi by n whole square. So the final formulation can be obtained as sigma xi square by n minus 1 minus of n times of sigma xi whole square divided by square of n minus 1, and this goes away, and we have finally n sigma xi square minus sigma xi whole square divided by n minus 1, so times of n, okay. So this formula actually simplifies the calculation. In any kind of a frequency table, it is important that you should be able to pull out a variable which can be useful and which can be very easily used for the calculations, etc. So let us say, for example, we want to describe a frequency table as given here. You have several different mid values of the interval x, and there is a frequency also which is distributed, or which is actually shown here. So basically the way that the mid value x equal to 24 to 424.5 would be operating is for 3 times, and this actually comes from the histogram analysis. 434.5 is 4 times, 444.5 is 10 times, so on and so forth. So having said that, now playing around with these different values, they are quite I would say cumbersome, And can we do something so that a simplified form of this value can emerge, which can be the basis of calculating our distribution, and then later on whatever simplified value has or whatever formulation has been done to obtain that simplified value can be used to reconvert this back into the original value, so that the mean value etcetera and all the standard deviation etcetera can be recorded. So, here we want to code this variable and make it into a coded variable v in a manner, so that the coded variable v is basically the main value. So, in this particular case, let us say for the observation number 1 or serial number 1, the main value is 424.5. Okay. So, we are actually trying to see how much different it is from the mean, and in this whole distribution it so happens that if you do the sigma f x by sigma f, you would get the mean value to be around 464.5 in this particular case, which is actually this particular value here. So, we are trying to take off this value every time. So, 424.5 minus 464.5 and then divide the whole thing by 10. Okay. So, this is the coded variable. Coded variable basically means, the v variable means basically the actual value minus the mean value divided by the factor of 10. Okay. So, now you have converted all these different values 1, 2, 3, 4 into their respected coded variables, as you can see v1, v2, v3, v4, so on and so forth. So, the as you can see, the coded variable is much simpler and it is very easy to calculate on the basis of the coded variable. So, you can use the frequency and the coded variable and do all the calculations as per the coded variable, and then whatever transformation you had used for obtaining this variable actual value minus mean value by 10, you just actually revert that back, so that you can get the original value. That is the whole idea. So, here the standard deviation, for example, can be represented as sigma f v minus v dash being the mean of the coded variable okay, square divided by sigma f minus 1. And if I just were to simplify this value, it would result in sigma f v square plus sigma f v dash square minus twice sigma f v times of v dash divided by sigma f minus 1. And in fact, if I further simplify this, this would result in a value of sigma x square equals to, let us just put the value of sigma f here as the total number of observations or total number of the subgroup size. This is n, let us say there are n observations, n is equal to 99, as you can see in this particular case. So, you can represent this by sigma f v square by n minus 1 plus sigma f v dash square by again n minus 1 minus twice sigma f times of v dash divided by n minus 1. And further, I would just like to illustrate here that the sigma x again can be more simplified as, now I just convert whatever we have in this expression right about here into a more simpler form for us to be able to calculate it through this table or this variable approach. And let us see what are the basic minimum values which are needed in terms of the frequency v, frequency f and the coded variable v in order to be able to calculate the mean and standard deviation of the distribution. So, I just write this down as sigma f v square by n minus 1 plus, and this becomes equal to, as you know, this is sigma f v dash square, where v dash basically is the mean value of the coded variable, which is a unique value. So, I can just simply write that you are merely repeating this n times, right. So, sigma f v dash square is basically meaning to say the v dash square times of 99, which is the sigma f value, v dash being uniquely common in particular distribution that we are considering. So, this can be represented as n v dash square by n minus 1 minus of twice v dash times of, you can write the value of sigma f v here by pulling out v dash outside the summation, and so we are left with, if we just allow this to come out, we are having sigma twice v dash times of sigma f v by n minus 1. And in fact, what I am going to do here is to sort of multiply and divide this value by n, where n can be represented as sigma f, so that I have a final expression sigma f v square by n minus 1 plus n v dash square by n minus 1 minus twice v dash times of n times of sigma f v by sigma f, which is actually equal to the variable v dash, as you may recall earlier. So this is actually the mean value of the coded variable distribution. So this can be replaced by v dash, and this you divide by n minus 1. So then you have again sigma f v square by n minus 1 plus n v dash square by n minus 1 minus twice, and you have n times of v dash square divided by n minus 1, and you can further represent this by, you can actually assemble them together as sigma f v square minus of n v dash square by n minus 1, or in other words sigma f v dash or f v square by n minus 1 minus of n times of this v dash value, which is actually sigma f v square by square of n times of n minus 1. This goes away in a similar manner, and this is the square of standard deviation sigma x square, I am sorry. So sigma x square then becomes equal to, simply speaking, the if you sort of simplify this more, you can have n sigma f v square minus sigma f v whole square divided by n times of n minus 1, or in other words the sigma x can simply be the under root of this particular term, n sigma f v square minus sigma f v whole square divided by n times of n minus 1. So all you need to do is to sort of now calculate on the coded variable what is the sigma f v square, and you also have to calculate what is the sigma f v whole square, and that can be very easily calculated by constructing two simplified columns, and in one column just multiplying the frequency with respect to the coded variable, another square of the frequency with respect to the coded variable. Remember, these coded variables are now very easy to handle computationally, and you can easily inexpensively calculate, and this is probably only showing few variables, but in actual cases there may be thousands and thousands of such variables, and so you now have the capability to quickly calculate the standard deviation sigma x from this distribution. In fact, the standard deviation can simply be calculated by using the formula obtained in the last step here, okay, which is n times of sigma f v square minus sigma f v whole square divided by n minus n times of n minus 1. So you can simply substitute these different values, 99 being n times of 297 minus of the minus 11 sigma v f square divided by n times of n minus 1 whole under the root, and so this comes out to be equal to, so the standard deviation of the distribution actually comes out to be 1.737. So having said that, in a very simplified manner, by using less computations, you are able to calculate what is the standard deviation of this particular distribution. It's the mean, for calculating back the mean of the distribution, you just need to revert back the transformation that had been used for doing the coded variable, however the standard deviation will remain same. So that is the premise that is used in all these circumstances. So having said that, I think we have a fairly good idea now of how to start plotting the x and r charts, and we will close probably this module in the interest of time, but in the next module we will actually start plotting these charts and learning more about these charts, particularly when we are talking about a quantitative description of a parameter, a quality parameter like a x bar or a r chart. So till until then, goodbye. Thank you.